The bar graph below shows how many students chose each flavor of ice cream on a recent field trip. What fraction of students chose chocolate ice cream? This is a basic interpretation of a graph, so chocolate looks to me like 11. And then the total would be the denominator. So that's going to be 11, strawberry, let's see here, 5. And then vanilla is 8. And everybody loves ice cream. And therefore, that would be 11 over 24. And that's basically all they're looking for in this question. In trapezoid ABCD, AB is parallel to DC, and angle DAF is 90 degrees. Point E is on DC, so that EB is equal to BC is equal to CE. Point F is on AB, so that DF is parallel to EB. In degrees, what is the measure of FDA? Okay, so EB is the same as BC, is the same as EC. So that's basically an equilateral triangle. So therefore, those will be 60s. So this question is what is known as angle chasing. You got to, chase the angles, I guess. And what do they want us to figure out? FDA. So FDA is this angle right in there. Okay, so hopefully we'll get there. Okay, so this angle here would be 180 minus that 60, so that's going to be 120. And then it's a trapezoid, so that means that's parallel to that. And there was another parallel. DF is parallel to EB. So DF, this one, is parallel to EB. Okay, so if that's the case, then that means that we can use that rule, that Z rule, this rule, where this angle is the same as that angle, if this is parallel to that. So that's 60, and then where can we go from here? Well, then, therefore, this would be 60, right? Since those two, this is parallel to that. And then therefore, this guy in there would be 30, since this is 90 degrees. Okay, so that's basically all it is. So angle FDA is 30 degrees. Line segment AD is divided into 3 segments by points B and C, so that AB to BC is 1 to 2, and BC and CD is 6 to 5. The length AD is 56 units. What is the length of AB? Let's label this. So AB I'll call X, and BC I'll call 2X, since that's what they've told me. And then the other guy, that is 6 to 5, so I'll call it 6Y and 5Y. Okay. And then BC has been represented by 2x and by 6y, so they're both equal, so therefore x is equal to 3y. And I think that should be sufficient to calculate this. So the total, which is x plus 2x plus 5y, they're telling me is 56. So yeah, I think that would be fine, because we've got this here, so we can substitute that in. So x is 3y, so that put that 3y in there. So that's going to be 9y plus 5y, and therefore that's 14y. And therefore y would be 4, and therefore that means x is 12. And what is the length of AB? Well, that's 12, since AB was represented by x. The series below includes the consecutive even integers from 2 to 2022 inclusive, where the signs of the terms alternate between positive and negative. What is the value of s? We have s equals 2 minus 4 plus 6 minus 8 plus 10 minus, I'm assuming, 12, and so on. And then it'll eventually be 2014 minus 2016 plus 2018 minus 2020. And then eventually this very last term, which is 2022. Okay, what I notice is that if you look at these pairs, they're all equal to minus 2. Right? Minus 2, minus 2. And then you have this 2022 hanging at the very end. So that pretty much, I think that's all there is to it, really. All I have to do is figure out how many of those minus 2s there are, and put that in the bracket, and then multiply that by negative 2. And then add that final 2022. Okay, so that's the discussion right there. How many of those minus 2s do we have? Okay, so let me think about this. So if you look at the original, it's every even number till 2022. So 2022 divided by 2 would be the total number. So that'd be 1 1011. That's how many integers are in that sum, this sum S. Now, I've paired those. I've put them in the groups of 2, but I didn't pair the last one. So let me get rid of that last one. So if I get rid of the last one, there's only 1010 integers. And those 1010 integers are put into groups of 2. So that would mean 505 pairs. Right? And each pair has a sum of -2. So 505 is what goes there. And therefore this would be minus 1010 plus 2022, and that is 1012. What is the largest integer n with the properties that n is between 200 and 250 and that 12n is a perfect square? N is between 200 and 250, and n is a perfect 12n is a perfect square. So 12n, they're saying, is some perfect square. So let's just call it m squared. Okay. Well, first of all, 12 is what? 2 times 2 times 3. And then n. Okay, so 2 times 2, that's already a perfect square. So this n has to have a 3 in it in order for it to combine with that 3 in order to give a perfect square. It could have other things, of course, it needs to, in order to be in that range. Okay. Okay, so let's take it one step at a time. And they're asking for the largest one. So let's start with the largest, which is 249, right? In that range. So the first thing, of course, is that the first thing, of course, is that the n has to be a multiple of 3, because it has to have a 3 in there in order to combine with that 3. Otherwise, it's not going to be a perfect square. So let's see, is 249 divisible by 3? And it is. Okay, so that's good. So this would be 2 times 2 times 3, and then n would be 3 times 83. Is this a perfect square? This is, but 83 is not. I think 83 is a prime number. Yeah. Okay, so that fills. No problem. Let's keep going. I'm going to step down to 246. The reason is because it has to be a multiple of 3, so it's pointless to look at 248 or 247. And that is 3 times 82. Okay, let's see what happens there. If I put that there, it'll be 3 times 82. And I think this also fails, because 82 is not a perfect square, so that fails also. Okay, no problem. Let's keep going. 243 is the next one. That's 3 times 81. Aha, I think we got this one. So that's 3 times 81. Yep. That's a perfect square. That's a perfect square. And I am certain that you know that 81 is also a perfect square, right? It's 9 squared. So the value that they are looking for is 243 for n. Each of the a, b, c, d is a positive 2-digit integer. These integers satisfy each of the equations. B equals 3c, d equals 2b minus c, a equals b plus d. What is the largest possible value of a plus b plus c plus d? So let's actually see if we can get that into one variable. It might be possible, and if so, then we can kind of work with that, considering that they're all 2-digit integers. Okay, let's see. So a plus b plus c plus d, this guy, well, a is b plus d, so let's put that in there, that first letter. B, let's keep b for now. C, according to this, would be b over 3. And d is this guy, 2b plus c, 2b minus c. Okay, let's see here. Let's combine these. Well, let me see here. B plus d plus b over 3 plus 2b, c minus c, which is b over 3. Okay, that's good. So then this cancels with that. So this could be 1, 2, 3, 4, 4b plus d. Okay, well, I got 2 variables. That's pretty decent. Can I get d in terms of b? Well, d is equal to 2b minus c, right? And then c is equal to b over 3. So therefore, And that would be 5b over 3. So I think we got everything in terms of one variable, 5b over 3. And that looks to me like 17b over 3. Okay, great. If I can maximize b, I can maximize that, because they want the largest. Okay, well, b is a 2-digit positive integer, and the largest 2-digit positive integer I can make is 99. So let's substitute 99 in there. 17 times 99 divided by 3, and that's going to be 561. But here's the thing. I have to make sure that this 99 is actually legit. And what do I mean by that? Does it fall under the parameters? Like, for example, are these satisfied? Because I can't just choose 99 and think, okay, I'm done. It's got to be valid. So let's see if 99 is valid. If it's not, then this is wrong. Okay, so let's see here. A is b plus d, correct? So that means a would be, again, I have to try to get it into one variable. B is 3c, and d is 2b minus c, entirely based on that. And then that's 3c, and then 2b is going to be 6c, right? I think. Yeah, sorry, that's a 3 there. So this is 8c. Okay, so, well, a is a 2-digit number, so that means it's between 10 and 99. And a is equal to 8c, so 8c is also between 10 and 99. So I've got to divide through by 8 in order to get the parameter for c. You see what I mean? You can't just choose something and think that it's okay. So this, as you can see, it narrows my c down pretty much to be between 1.25 and 12.3, and really it's even more narrow than that because c is a 2-digit number, so it can only be 10 or 11 or 12. Now the way I've done it here is I've done it for b, so let's see what the parameters are for b. If I continue here, c is equal to b over 3. So that would mean, in order to get b, let's multiply through by 3, so it'll be 3.75 b, and that'll be 36.9. Aha! So the largest b is not 99 like I chose. 99 is invalid. The largest b, according to this, would be 36. Yeah. So it's very important to do that. Okay, so then now let's revisit that 17b over 3. So that'd be 17 times 36 over 3. And that's 204. And this is the correct answer. What is the sum of the digits of the integer equal to 3 times 10 to the power of 500 minus 2022 times 10 to the power of 497 minus 2022? Well, the first one, 3 times 10 to the power of 500 minus 2022 times 10 to the power of 497 minus 2022. Okay, let's do this one step at a time here. This basically is 3 followed by a whole bunch of zeros. And how many zeros? 500. So that's the first guy. This one is 2022 followed by a whole bunch of zeros. And how many zeros? 497. And then this is just a 2022, so that's pretty straightforward there. Okay, so let's talk about this now. If it's too daunting, what you can do is just sort of use a smaller example. Like just use 30,000 and then 2022 like that, and then see what it is. Just to kind of get an idea. But here's the thing. First, I got to match up the digits. This whole thing would be 501 digits, correct? Because you have the 3 and then you have the 500 zeros. This whole thing is 4 digits there and then 497. That's also 501. Okay, good. So that means that the digits match up. So basically what that means is one of these scenarios. Yeah, so I was right on the right track there. Let me just think about that for a second. Yeah. Okay, so if I do this, it'll be 0, 0, 0, all these zeros. And then eventually, it will be, oh oh boy. Let me think about this for a second. 978, I think. 978, like that. Yeah. I'm pretty sure that's right. But the key thing there is that's one digit less. What? Yeah, so there's 500 digits in there. Like these guys were 501, but this drops down to 500. So that's important. Yeah. Okay. So we took care of this guy and this guy. Now we have to, of course, concentrate on this. So we got to take this number here. Let me just write it again. 978 and then a whole bunch of zeros. And then subtract from that this 2022. Okay. Again, this, obviously, you're not going to type this into a calculator because this has 500 digits. But what you can do is you can put in a smaller number. Put in something like, something like this. Six zeros. And then subtract 2022. And see what you get in your calculator. And then do that for maybe one more zero. Yeah, like that. And then subtract 2022 like this. And see what you get. It'll give you an idea. And what happens actually is you get this. You get a 977. And then you get a whole bunch of nines. ... 999. And then at the end, you will get a 7978. Okay? And like I said, if you do these kinds of, smaller subtractions, you'll get an idea of what this looks like. Okay, so now we have to find out how many digits is this. And you'll notice that this is also 500 digits. So this was 500 digits up there, this guy. This is also 500 digits when you do the subtraction. Okay, well, this is 3 digits, and this is 4 digits. So that means these must be 500 minus 3 minus 4, which is 493. 493 of those 9s. So now they want the sum of the digits. Okay, that shouldn't be a problem. Sum of the digits. So we got the 9, we got the 7, and the 7. And then we have 493 of those 9s. And then finally we got that 7, these guys, the 7, the 9, the 7, and the 8. And then if you do this, this will be 33, sorry. Gotta make sure I do the math correctly. So 23 plus 4437 plus 31, and that is 4491. So there you go. 4491 is the correct answer. The integers a and b have the property that the expression 2n to the power of 3 plus 3n squared plus an plus b over n squared plus 1 is an integer for every integer n. What is the value of the expression when n is 4? So we have to do something called fancy algebra. And these kinds of questions are actually kind of common. And you'll hopefully see what I mean by that. We got to keep doing a little bit of fancy algebra to get it into a form that allows you to see if it's an integer or not. Okay, so this is the original expression. So let's begin. Here we go. So the first two terms I will leave as is, and then I will add a 2n minus 2n. And really the attempt is to factor. We're trying to factor. That is our goal here. And you'll hopefully see that kind of come into play as I proceed. And then this an plus b I sort of leave. So I really just did that. And I know right now it seems a little pointless, but hopefully you'll understand. And this n squared plus 1 I'll just add at the end. I don't want to keep writing it again and again. I'm just going to concentrate on the numerator for now. So now we are going to regroup this a little bit. So this 2n, this guy and this guy. And then this 3n squared minus 3. So this one and which one was it? This one, this minus 3. And then the an minus 2n. And then finally the b minus 3. Hold on a second. I think I did something wrong. This should be the plus, sorry, and that should be the minus. Okay. I think it's all well accounted for. Okay, so now I can factor. So this one, 2n, n squared plus 1. And then the 3n squared plus 1. And then from here, n, a minus 2. And then the b minus 3 sort of just hangs out by itself. And then now the n squared plus 1 and 2n plus 3. And then na2 plus b minus 3 like that. Okay, so that, and I know it doesn't seem like anything great, but remember it was all over n squared plus 1. Now, when that happens, this cancels with this to give you just 2n plus 3. And then we have this na minus 2 over n squared plus 1, because that the denominator still is valid there. You can't cancel it. And then b minus 3 over n squared plus 1. Okay. So now that we've got this into this nice form, let's discuss this now. The question is basically saying that this expression is an integer for all values of n. So this whole thing is an integer for all values of n. No matter what you put in for n, it's going to be an integer for every integer n. But here's the thing. What's a and b? What is a and b? Right? We don't know that. If we have that, then we can easily solve the question, because eventually they're telling us to just sub in n equals 4, which is no problem. But I need to know what is a and b. Okay, well, let's take this one step at a time. So this guy here, no matter what n is, that's always going to be an integer, right? Because n is an integer. Every integer n. So no matter what I put in for n, that 2n plus 3 is always going to be an integer. So that's taken care of. We don't need to worry about that. Well, to figure out what is the value of a and b, we got to look at these expressions individually. So let's do that. First, let's look at this guy, and then let's look at that guy. So here we go. So eventually I will have the value for a and b, and then I can just figure out that value of that expression. So let's take this one step at a time. So first let's look at a minus 2 times n over n squared plus 1. Okay, for that one, we need to make these into integers. So this has to be an integer. Well, if a equals 2, that will be a 0. So that's a very good candidate, right? If I sub a equals 0, that becomes 0, and 0 is an integer. But what if a does not equal 2? Okay, so let's say a equals 3. If a equals 3, then I plug that in, it'll be basically n over n squared plus 1, right? If I plug a equals 3. Well, this has to be, according to their definition, an integer for all values of n. But I can prove that it's not an integer just by putting in n equals 1. It becomes 1 over 2. So therefore, not an integer for all n, for every n. In a very quick way. So a equals 2 is the only value for which that term, this guy, is an integer for all values of n. Okay, so the same story we do for b. And that's this one, b minus 3 of n squared plus 1. If b equals 3, then that becomes 0, and it's an integer. Okay, b equals 3? Yeah, b equals 3. But what if b did not equal 3? Say b equals, say, 4. What happens? Well, then the numerator becomes 1, and it becomes 1 over n squared plus 1. And if n is 1, then this basically becomes a half. So therefore, again, it's not an integer for every n. So very quickly, you can figure out that a equals 2 and b equals 3. And therefore, since n equals 4, when you plug all those guys into there, it really just reduces to 2n plus 3, because this and this are 0. So you can put that in if you want, plus 0 plus 0. So 2 times 4 plus 3, and that is 11. So 11 is the answer to this question. Three circles with centers A, B, and C have radii root 3 minus 1, 3 minus root 3, and 1 plus root 3, respectively. Each circle is externally tangent to the other two as shown. The area of the shaded region is of the form a root 3 plus b pi plus c pi times root 3 for some rational numbers a, b, and c. What is the value of a plus b plus c? Well, the first thing I thought of immediately is the Heron's. You guys know about Heron's formula, right? And that basically states that if you've got some triangle and it's got the sides A, B, and C, then the area is equivalent to S times S minus A times S minus B times S minus C, all under the square root sign. And what is S? Well, S is basically the semi-perimeter, so A plus B plus C over 2. And therefore, if we were to do that on this triangle, the A would be root 3 minus 1 plus 1 plus root 3, so that's 2 root 3. The B would be 1 plus root 3 plus 3 minus root 3, so that's 4. And the C would be root 3 minus 1 plus 3 minus root 3, which of course is 2. So if I put that into Heron's, it would basically be root 3 plus 3 times root 3 plus 3 minus 2 root 3 times root 3 plus 3 minus 4 times root 3 plus 3 minus 2, all under the square root sign. And if I rearrange this, it'll be 3 plus root 3, and then if I do all the other guys, 3 minus root 3, root 3 minus 1, or root 3 minus 1. Okay, that's pretty decent. So this is basically 9 minus 3 times 3 minus 1, and that looks to me like 6 times 2, so that's root 12. Okay, the area is root 12. That's pretty good, actually. It didn't take that long. But here's the thing. Then I look closely at this. This is not a full triangle. They just want the shaded region. So that means I've got to subtract from that triangle this little pi segment. Okay, that's why the area has these pi's in it. Okay, I understand. Okay, so in order to subtract that little pi segment, I have to know what this angle is. What is that angle in there? Now, how do I figure that out? Do I use cosine law? And this is what I think. Let me just see what happens here. Cosine law, yeah, cosine law would be fine, but that's, it probably wouldn't take that long either. But let me see. I'm thinking that might be 90 degrees because of the way it looks. So let me just see. If a squared plus c squared is in fact equal to b squared. A is 2 root 3 and c is 2, right? So that would be 12 plus 4, which is 16. Aha, and b is 4, so there you go. Yeah, it is. That is a right angle. So that means theta is 90 degrees. That's very helpful. I probably could have figured that out with the cosine law anyways. But that means that this area of the shaded region, we'll just call it AS, area of shaded region, is this root 12 minus that pi segment, which is basically pi r squared times theta over 360. So that's going to be, let me think about this for a second. Yeah, I think that's correct. Well, root 12 is what, 2 root 3? Yeah, 2 root 3 minus, and then which r are we using here? We're using the smallest one, right? So that's, of these three, which is the smallest? 1 plus root 3, that's 2.7. 3 minus root 3 is 1.3 approximately, and root 3 minus 1 is about 0.7. So we're using this guy here. So root 3 minus 1 is what we're using. So pi root 3 minus 1 all squared. And then that's 90 over 360, which is a quarter. So there we go. We got it. And then, of course, I have to expand this, and I have to make it into this form here. A root 3. Let me just put that here. A root 3 plus b pi plus c pi root 3. Okay, so I have to get it into this form, and then that will allow me to figure out what is a, b, and c, the values of a, b, and c. All right, so let's expand this. So 2 root 3 minus, let me just put this in brackets for now, pi 3 minus 2 root 3 plus 1 all over 4. So that's going to be 2 root 3 minus pi times 4 minus 2 root 3 all over 4. Correct? And then so 2, and let's get rid of those 4. So this will be pi 1 minus root 3 over 2. So in the end, it will be 2 root 3 minus pi plus root 3 over 2 pi. And hopefully I did that correctly. Yeah. So now let's match it with this guy. So that means that since this is a root 3 plus b pi plus c pi root 3. So let's carefully match this up here. So that means a is 2. Okay. B looks to me like -1. And the c is a half, I believe. Okay. So then therefore a plus b plus c would be 2 minus 1 plus a half. And that is 1 plus a half, which is 3 over 2. Starting with 4-digit integer, a 4-digit integer that is not a multiple of 1,000, an integer with fewer digits can be obtained by removing the leading digit and ignoring leading zeros. For example, removing the leading digit from 1023 gives the integer 23. Removing the leading digit from 2165 gives 165. How many integers from 1001 to 4999, inclusive other than the multiples of 1,000, have the property that the integer obtained by removing the leading digit is a factor of the original integer? All right. So first of all, n is between 1001 and 4999. So that's my parameters. And not a multiple of 1,000. So well, 1,000 is not even in there, so no need to worry about that. So it's not 2,000, it's not 3,000, and it's not 4,000. So those numbers you're not going to include. Before I get into this, let me just give an example of what they're talking about. And I think an example would be 1,500. Let me explain. So when you remove the leading digit, which in this case is 1, the number you are left with is 500. And that is indeed a factor of the original number. So exactly what they said, you remove the leading digit, and the integer obtained by removing the leading digit is a factor of the original integer. So this is the number we get when we remove the leading digit, 500, and the original number was 1,500, and 500 is indeed a factor of 1,500. So this is just an example, and I'm sure there's many of these. So we got to figure out how many. Okay, so that's a lot. So we got to think of a system here. Well, what I will do, I think, is I will break it up into regions. Oh, I don't know if region is the right word, but for example, 1,000. I got it. I think n is between. So n is between 1,001 and 4,999. Okay, so I'll look at what is the leading digit. So for example, the leading digit, n is between 1,001 and 4,999, right? Okay, so let's look at the leading digit. I think that's the right way. So the leading digit is 1. So the number is of the form 1 and then 3 numbers after it. So whatever it is. And then those three numbers after it, this guy, whatever you want to call it, let's just call it, I don't know, M, let's say. That M is actually between, the small, it can't be 0, so it's got to be at least 1, and it's got to be less than 999, right? Yeah. Okay, so let's start off with an example. Let's say we have 1,500. Just like our example here, I think that'll be sufficient. So that basically is 1,000 plus 500. So this is sort of my M. And in order for this to work, this 500 has to be a multiple. Sorry, it has to be a factor of the original number. Yeah. Or another way of thinking about it is that the original number has to be a multiple of this number. So we could say k times 500. Yeah. So that means, like in this case, it'd be 1,500 is 3 times 500. You see what I mean? I'm doing it in numbers first, because if I go straight to letters, it might be a bit abstract. So if we were to rewrite this, it would basically be 1,000 is equal to 500k minus 500. So 1,000 is 500 times k minus 1. Okay, that's great. So, but I want to have some kind of a formula that for all numbers. So, for example, for all of these m's. So it's going to be 1,000 plus m is equal to k times that m, right? Doing the exact same thing, but this time just for all m. And therefore 1,000 would be k times m minus m. And therefore 1,000 would be equivalent to, factor out the m times k minus 1. Got it? So that means that the original number 1,000 is a multiple of m. And m is what you get when you remove that leading digit. Yeah. Okay, I think that's a good start. So let's see now. So that means that in order to get m, it has to basically be a factor of 1,000, according to this guy right here. Okay, so what are the factors of 1,000? There's a quick way of figuring out factors of a number, how many in fact there are. So what you do is you first break it up into its prime factors. So in this case it's 2 to the power 3 times 5 to the power 3. And the number of factors is done really quickly. You take this number, which is 3, add 1. Take this number, add 1, and you multiply them. So this would be 4 times 4. So there's 16 factors. But don't include the 1,000, because remember, 1,000 cannot be included because it cannot be a multiple of 1,000. That's kind of a little bit of a trick. So therefore, there's only 15 that you have to consider. Okay, so we'll eventually have to figure out the total, and 15 is part of the total. Okay, pretty good, right? All right, so let's keep going. We did that for a leading digit of 1. We've got to now do that for a leading digit of 2. Okay, so let's do that for a leading digit of 2. Similarly, so in a very similar way, similarly, is there a I in there? I don't know. So we will get this. We get 2,000, just like we had here. We'll get 2,000 this time is equal to m times k minus 1. And very similarly, m is a factor of 2,000. So same thing, you break up 2,000 into its prime factors, which I believe is 2 to the power 4 times 5 to the power 3. The number of factors, therefore, in our quick system would give me 4 plus 1 times 3 plus 1, which is 5 times 4, which is 20. But don't include 1,000 and 2,000 because those are multiples of 1,000. So really it's 20 minus these two, so 18. So 18 is how many we get from the leading digit of 2. So hopefully that's you're getting the hang of this. So let's keep going here. And now we get the leading digit of 3. So leading digit of 3. Okay, so same thing now. 3,000 is equal to m times k minus 1. And 3,000 is what? Is it 3 to the power of 1, 2 to the power of 3, 5 to the power of 3. So this time the number of factors would be 1 plus 1 times 3 plus 1 times 3 plus 1. And that's what? 32? Yeah, 32. And then who do we have to get rid of here? We got to get rid of 1,000. We got to get rid of 3,000, and then we also have to get rid of 1,500. Now, why? And they say, well, that's not a multiple of 1,000, because if you remember, the m is only between 1 and 999. So the factors can't be greater than 999. So then 1,500 is a factor greater than 999. So that's why you got to get rid of that. So these three have to remove for that 32. So it really just comes down to 29. And that 29 is going to be added to our running tally. And then we got one more leading digit. So leading digit, the last one is 4. And by now, hopefully you're an expert. So it's 4,000 this time is equal to m times k minus 1. And therefore 4,000, well, what's that? Prime factorization, 2 to the power of 5, 5 to the power of 3. So the number of factors would be 5 plus 1 times 3 plus 1, which is 6 times 4, which is 24. But we got to get rid of some stuff. We got to get rid of 4,000, 2,000, and 1,000. Anything else? I think that's it. So if you get rid of those three from this 24, you get down to 21. So 21 is the final piece of the puzzle. And when you add up all those guys, you get 83. So 83 is the final answer.